Good morning, everyone. My name is Adrian Woodhead. I'm a developer at hotels.com. This is my colleague, Elliot West. I've got some people frantically trying to break the doors down, which is good. So today we're going to be talking to you about tools and approaches for migrating big data sets to the cloud. And this is based on our real-world experiences about 2 years into a very large-scale cloud migration. So very briefly, an overview of what we're going to be talking about today. We can talk a little bit about why the cloud, why we decided to move there, and kind of a high-level overview of our plan for the migration. We're then going to talk about the first sort of set of hurdles we had, which was about migrating massive data sets over into the cloud, and then a tool we built and open source, which is called Circus Train, to do that. We'll then talk a bit about, once we were in the cloud, some of the issues we had around sharing data across different accounts. And then again, another tool we built and have open source called Waggle Dance, which allows you to do Hive query federation. And then finally, we're going to wrap up with some of the lessons we learned, some of the patterns we came up with, which I think have made our lives a lot easier and given us a lot more insights with how we work with our data in the cloud. So just very briefly, this isn't a marketing slide, although it might look like one, so please, all the developers, don't run screaming out the door just yet. This is actually important because the way our company is structured actually had an impact on how we ended up building things later on. So Expedia, it's the company we work for particular hotels.com. But as you can see, the company is made up of lots of different sort of sub-companies, brands, that have been acquired over the years or built out. And some of these parts of the company have been in existence for like 20, 25 years. So we've got a big presence our technology presence is very big in terms of physical data centers. We've got thousands of machines. A lot of our technology predates, the cloud even existing. So that's kind of where we are today. And then over the past few years, like I'm sure many other people in the room, we've been thinking, what advantages do we get by moving to the cloud? So obviously lots of different reasons. I'm just going to go briefly through the three that were most appealing to us. So the one that gets talked about the most is the cost. So obviously, if you've got your own data centers, your own hardware, you're having to, manage all of that. One, two. There we go. Yeah, brilliant. You're having to manage the cost of all of those machines, upgrade the hardware, replace it, all the operation staff involved with that. And the idea, obviously, of moving to the cloud is the cloud providers do that for you, but on a massive scale across all of their customers. So you benefit from having those reduced costs. As developers, what is more interesting to us is being able to get our hands on new technology sooner. And where we really notice this is in the big data processing side of things, where we mainly focus, is today we have a shared Hadoop cluster, which is hundreds of nodes running in a data center, and we have the entire company using that cluster. So what this means is, operationally, that makes quite a bit of sense because we can kind of share that resource across the company. But what it means is whenever we want to upgrade Hadoop to get like a new version of something, we have to get all the users to agree to it. So you might have like parts of the company like us that want to use the latest things all the time. And then there might be another part of the company that's much more conservative, and they're a bit like, don't touch anything, it works, just leave it alone. And then we have this constant tension whenever we want to do an upgrade. And we have to get everyone to agree, everyone to test, go through this big procedure. And what this really means is upgrades are few and far between. So the idea of moving to the cloud is, you've got a lot more technology available. The cloud providers upgrade things a lot quicker. Different teams can move at different speeds. So that's obviously very appealing. Another key aspect of the cloud that's very attractive is the elasticity of it. So again, if we think about that Hadoop cluster, there are times, like on the weekend, for example, when a lot of people aren't using it, they're probably just data processing jobs running. We have hundreds of machines that are being underutilized, but we have to pay for them. And then the flip side of that is at busy times of the week or the month, we have a lot of data processing jobs running, we've got a lot of people running queries, everything slows down, and then everyone's moaning, like, why isn't my job running fast enough? So again, in the cloud, you can obviously much easier, just instead of having to buy machines and set them up, you can just tick a few boxes, spin up your cluster, add a few hundred nodes, do your data processing, tear them down again. So if we then looked at, okay, we're going to move to the cloud because of all of those reasons, what does that actually mean on the data processing side? So if you kind of look at our data warehouse, we have well over a petabyte of data spread across hundreds of data sets. And then we have thousands of data processing jobs connected in all kinds of weird and wonderful ways which produce those data sets. We're going to focus, just for this talk, we're going to focus on the data sets we have that are on our distributed file system, HDFS, and then have a Hive metastore on top of it for describing the data. And these data sets, again, because we have so many different users, we have all of these different file types. We have text, we have CSV, we have ORC, we have all Avro, basically if there's a Hadoop file system, we're probably using it somewhere. Similar to that, the data processing tools that we use, we've got MapReduce, we've got Hive, we've got Cascading, we've got Spark, loads of different frameworks accessing the data. And then we also have a very wide variety of different users. We have data engineering teams, we have analysts, we have data scientists, we have people processing data in a batch manner. We have other people who want to get the data in near real time out into bidding engines. So there's a whole lot going on here that would need to be migrated. So we kind of stepped back and thought, okay, if we're going to be doing this, let's think about how are we going to do this. At a very simple level, we have some jobs that produce data sets that are used by users. So that seems fairly straightforward. But then we looked at, okay, if we looked at migrating the jobs from our on-premise cluster into the cloud, which in our case, we've chosen to go with Amazon. But most of what we're covering here today, the concepts are the same for different cloud providers. But yeah, if we went for the jobs first, that's a massive tangled web that would need to be sorted out. So we figured, let's flip this problem on its head, and maybe we'll focus on migrating the users to the cloud first. So our data scientists were actually the group of users who were pushing for this the most because they wanted to get their hands on a lot of the new tooling that's out there. So if we put them in the cloud first, they'd be there, they'd be able to use all the cloud technology, we'd be able to unlock some early business value, fantastic. But obviously having users in the cloud without any data is a bit useless. So we need to find some way of getting the data to them, but we can't change the jobs. So what do we need to do? We need to replicate the data into the cloud. So the idea here is we would have the data being processed on-premise, produced there, we replicate it into the cloud, and now we have the same view in both places, on-premise and in the cloud. So people can use it from there, we migrate them over. And then this frees up our engineering teams now. They don't have this pressure to get their data sets migrated over. They can spend a lot more time deciding how they're going to do their migrations of their jobs, whether they're going to lift and shift them, whether they're going to re-architect them. So they can take time, and hopefully this will produce a better migration. So ideally, over time, the jobs get migrated over, the data sets migrated over, we turn off everything on-premise, and everyone's happy in this brave new cloudy world. So practically what this means is this whole process is going to take years. This isn't something, we can't just turn everything off and move it. It's going to take years whilst we do all of this. And whilst this is happening, all of those data sets are going to be changing just like they do today. We have updates coming in daily, hourly. So we need some way of being able to get that data replicated continuously so that the data that's available in the cloud is as similar to the data that's available in-premise today. So if we then focus just on that data set replication problem, what does that actually mean? So we have data on HDFS, and in our case, because we're going to Amazon, we want to move it over to S3. And data without metadata isn't that useful, so we need the metadata. So we have a Hive metastore on-premise, and we're going to run a Hive metastore on EMR. So those two need to go over. And then something that's very important for us is we need to make sure that this replication of data happens in a very coordinated manner. And what I mean by this is the data needs to be available first before the metadata, because you don't want people querying those data sets whilst they're in flight, because there might be partial reads, they'll get different results. So we need to make sure that that is done in a very coordinated fashion so that there's always a consistent view of these data sets. So then, in the time-honored fashion of developers everywhere, we thought we'll just look for an open source solution that does this for us. And we also work for a company that's happy to pay for a good proprietary solution. So this was about 2 years ago. We had a look what's out there, what's available in the open source world, what proprietary solutions are there. And we were actually really, really surprised at how few tools supported replicating the metadata. A lot of them just did the data. Not that many did the metadata, and virtually none of them actually did what I was describing there, doing it in a coordinated fashion so that you wouldn't get partial reads. It seemed like a lot of the tools were designed to do like a massive lift and shift and then you use it, but they weren't designed to be constantly replicating data whilst people are actually querying it. So nothing really ticked our data consistency box. We then had a few extra challenges on our side, which were maybe a bit more unique to us. So the version of Hive we were running on-premise was old. So there's some inbuilt replication features in Hive that are available today, but they weren't available to us because we had this old version. We also, because our teams aren't the people administering our Hadoop cluster, we don't have root access. So we couldn't build our own metastore hooks into the metastore. So we needed a solution that could run like as a normal user outside of needing root access. So there was nothing out there at the time that met all these criteria, so we reluctantly moved on to looking into what would we need to do to create our own replication solution. So the first challenge always is coming up with a name for your project. So we decided to call our replication solution Circus Train, and this is kind of keeping with the whole Hadoop elephants big top theme. And we also reasoned we were taking a crazy data circus from one location to another. So what does Circus Train do? When it runs, what it does, the first thing it does is it looks in your metastore. It finds out the metadata about the data that you're going to be replicating. And what this usually involves is finding the locations on HDFS that your data's where it's found. And then it starts reading that data and using a distributed copy mechanism, it starts copying that data over to S3 via a cluster of some sort, so EMR. And then in order to guarantee this data consistency, what it does is whenever it replicates data over, it puts it into a unique snapshot. So every time it runs, there'll be another snapshot. I'll talk about that in a bit more detail later. Once the data has successfully been replicated, it will then replicate the metadata. And by default, it just does a very simple transformation on that. It'll change the data location, so they're no longer pointed HDFS, they're now pointed S3. Once that's successfully completed, it'll then send a notification. By default, it'll use Amazon's simple notification service for this, so you can then trigger a downstream job based on the data being available. So at a practical level, what it looks like, this is a configuration file for Circus Train. You can configure it in different ways. This is just a nice YAML version of it. So what you do is you give it the metastore URIs of the thrift metastore endpoints on the source side and on the replica side, so Circus Train knows where to copy from and to. Here we're just configuring one simple table replication. You can configure multiple if you wanted. And here we're saying we've got a database called ETL in Hive, a table name called clickstream. And in this instance, it's a partition table. You can also do entire tables if you want. It's a very big data set. We don't want to replicate the entire thing every day, and typically only the last day changes in between runs. So you can provide a partition filter, and what this is saying is there's a partition column called LDate. Let's just say it's the landing date. And basically, we just replicate the last day's worth of data every time it runs. We then put the base location on S3 where the data is going to get copied to, because it needs to do that to repoint the data. And finally, for the event listener, we give it a topic that it'll publish events to. So then I'm going to talk a little bit about some of the more advanced features in Circus Train that some of the other tools out there that do this kind of stuff lack. So I mentioned we have this distributed copy mechanism. So this is configurable. You can write your own. But out of the box, it comes with standard Hadoop distcp. That's typically if you're going from HDFS to HDFS. We've written our own optimized version of this, which if you're copying to an S3 file system, so from HDFS to S3, for example. And that uses Amazon's S3 APIs to do the copying. What's kind of interesting about a lot of these copiers, another thing you need to think about is where you actually run the copy operation from. It's a distributed copy, so it runs on a Hadoop cluster. So it actually runs as a MapReduce job to do the copying, so you spread that out across your cluster. And you kind of have two options there also. You could run it on-premise and push the data out to the cloud, or you can run it in the cloud and pull the data in. And we found the latter was actually generally more efficient. It depends a lot on your networking setup between your data centers and the cloud. But if you run it in the cloud, you can basically get slots immediately. You don't have to wait for all the other stuff that's happening on your on-premise cluster in order all the contention that you might need for MapReduce slots. Another copier that we ended up building later, which was quite interesting, is the S3 to S3 copier. So that's if you're copying data between regions in Amazon. We actually use Amazon's S3 APIs, and we also use Amazon's infrastructure to do that. So they do the copy in the background, so you don't even need a cluster if you're doing that kind of copy, which is pretty cool. And then we kind of ate our own dog food recently, so we built our own copier using this plugin mechanism that we designed. And we've written a copier that takes data out of Google's BigQuery and pulls it back into S3 and Hive. Another feature that's really powerful when you're working with datasets on this scale is being able to limit the amount of data that you replicate on each run. So what I mentioned before, being able to provide partition filter expressions. So we use Spring's expression language for that. So this is the example I showed you earlier where we're just doing the last day's worth of data, but you can come up with much richer expressions if your data's formatted in a different way, and it'll only replicate that data on each run. We found we had certain very large data sets that changed in such a way that you couldn't actually write a partition filter to capture what the change was. So we've added another feature, which we call a Hive diff. And what that does is when you run it, it looks at the metadata on both sides, and then it actually looks at the files on both sides, figures out what's changed, and then it'll only replicate those bits. So again, that makes things much more efficient. And then this, I think, was our key feature that we spent a lot of time on, and this is using these snapshots in order to prevent partial reads of the data whilst the replication's in flight. And it also overcomes some of S3's eventual consistency issues. So the way this works, what I'm describing here, for this example, let's just imagine we're replicating an entire table on each run, but it applies equally well to partitions within a partitioned table. So the first time Circus Train runs, it finds a table, it creates a location on S3 called snapshot 1. The actual location is a bit more complicated than that, but just for this example, let's keep it simple. So the data gets replicated over. Fantastic. It then updates the metastore and tells it about that location. The second time you run it, it'll create a new snapshot folder. Let's call it snapshot 2. Replicates the data over into that. Updates the metastore to point the data locations to there. And let's say at that point in time, your users now start using that data. So they go to the metastore. It tells them the locations of the data are in the snapshot 2 folder. Your ETLs, your queries, data processing jobs can now all start running, and they're accessing data from that location. So whilst this is happening, you kick off another replication. So what it'll do then is it will replicate the data into snapshot 3, and that's invisible to all of those running jobs because we haven't updated the metastore yet. So they just carry on running as they are before. They're not going to get partial reads. And then we update the metastore to point the location to snapshot 3. Time passes. Any new jobs that come along now, they will start getting data from the snapshot 3 location. And over time, all those jobs that were accessing the data from snapshot 2 end. So at some point in time, nothing is using snapshot 1 or 2 anymore. Nothing's pointing to that data. It's effectively become orphaned. So we have a feature in Circus Train called housekeeping, which keeps track of this over time, and you can configure the amount of time that needs to pass, after which it will delete that data. So you won't be wasting space on S3 and incurring costs for it. A few other features, I'll go through these a bit briefly. We don't have time to go into all of them in much depth. So we've tried to architect it to be as pluggable as possible, so you can customize it in different ways if you need to. So a couple of examples of that notification mechanism I talked about earlier, where you can send messages to SNS. You could write your own if you wanted to send notifications to some system that you're using. Similarly, Circus Train gathers a lot of metrics whilst it's running, so all Hadoop counters, success failure, bytes replicated, etc. And by default, we provide a mechanism for sending all of those metrics to Graphite, but you could write your own if you wanted to if you use some other system. By default, it copies all the data and the metadata, but we have different copying modes. So we have certain use cases where it's useful to just mirror the metadata or make a few changes to the metadata whilst it moves over, but you leave the data in place. So there are a few of those that you can use. We provide support for replicating Hive views as well as tables. There are also various ways you can transform the metadata whilst it's in flight. So you can write your own custom transformations. So we found this useful. We had a data set on premise that was JSON formatted data using a very old SERDI in Hive. And when we moved it into the cloud, we wanted to use a newer JSON SERDI. So we wrote a transformation which just changed that in the metadata. We also had a lot of fun with all of this when we started off and we didn't have all the firewalls configured optimally between our data centers and Amazon. So we needed to set up a lot of tunnels, especially so the metastores could see each other. And this is something you could obviously set up outside Circus Train, but we needed to do it so much, we just made it a core piece of Circus Train, so you can just put a bit of configuration in with your tunnel routes. We store all the credentials in key stores. It's quite interesting. Some other distributed copy mechanisms actually output your usernames and passwords and credentials in a plain text in log files, so we don't do that. And there are a whole host of other features, but I think these are the key ones that are good to know about. So if you look at where we are today, having run Circus Train in production for well over 2 years, we have our core end-user datasets that are constantly being replicated over to the cloud. It's probably 150, 200 datasets at least, with more being added as more and more teams get involved. We've replicated well over a petabyte of data, and we're probably replicating, even just selectively replicating what's changed, we're probably doing tens of terabytes every day. It's being widely used across all of Expedia, and we've actually built a couple of other tools on top of it to integrate it into other parts of our tech infrastructure. And we've made some good progress at moving our analysts and data scientists over to the cloud, so they're able to use all of these new features and tools. And our engineering teams can now take a bit of time and look at how they're going to start migrating their jobs over. And we contributed it to open source. There's a short link to it, and we have links right at the end also to the project pages on GitHub. So you think, fantastic, job done, everyone's in the cloud, we've got a replication solution, we can all go home now, but this isn't quite the case, because this would be a very short talk if it was. So I'm going to hand over to my colleague Elliot, who will talk a bit about the next set of challenges we had once we were operating in the cloud.
Thanks. So as Adrian mentioned, our migration to the cloud enabled our users to innovate in new ways. But the cloud also became this rich source of new problems for us as well. So I'm now going to describe the next problem that we faced when we were there. So our earliest adopters of the cloud were our data scientists, and they couldn't really wait for us to perform our data platform migration. So they went off ahead to AWS. They set up their own AWS account. They spun up their own cluster infrastructure, Hive, Hadoop, and that was great. It gave them an early head start. They could start working on the problems they needed to solve. And then later on, we came along and we started migrating our on-premises data platform. So we too set up our own account. We set up our own cluster. And there we started to migrate those core datasets over from our on-premises cluster. Now, understandably, once we started doing that, the data scientists, they wanted access to those core datasets. And it was at this point that we kind of realized that we had overlooked something about having one large on-premises cluster. So when you have one cluster for your whole organization, it makes some things really, really easy. So all of your data is in one place. So if you want to explore data sets, discover and share data sets across your organization, it's really easy. Exploration is just a matter of browsing a single data catalog. And if I want to share a data set, all I need to do is just provide a fully qualified table name to whoever wants to use it. But in this new architecture that was forming in the cloud, we now had these multiple clusters and multiple accounts. And this was a problem because Hive and the frameworks that build around Hive, such as Spark, they have no provision for bridging multiple clusters or accounts even. So when we looked at this problem further, we saw that there are further cross-cluster dataset dependencies. So we, Hotels.com, are a consumer of Expedia datasets. And unsurprisingly, they too had done a cloud migration. They too had set up their own account and had their own cluster, and this is where they kept the data sets that we needed to get access to as well. And when we started to look at the roadmaps of other brands for their cloud migrations, we saw that this was just going to get worse. There were going to be more accounts, more clusters. So with this new kind of distributed architecture in the cloud, what we were actually doing was creating a set of data silos. And this is really going to inhibit us in terms of being able to leverage our data to the full. And so we could potentially miss out on some good opportunities there. So how could we solve this? Well, as I mentioned, it seemed to be quite good on premises. Everything was really easy to access. So maybe we could apply the same model in the cloud. Maybe we could unify all of those disparate accounts into one large account, spin up one massive set of infrastructure, and put all the data sets in there. Well, this just wasn't going to happen. We were trying to escape from this model. And it turns out as well that having multiple accounts is actually, for an organization our size, is a recommended best practice from Amazon. As an account owner, you're free to then set up your account to meet your use cases, and also segmenting accounts allow you to limit the impact of events such as intrusions into an account. It limits the blast radius. So we weren't going to do this unification. So what about replication then? Adrian was talking about Circus Train, a tool that allows you to make copies of datasets. Maybe we could replicate these datasets in the different accounts. This is certainly technically possible, but there are some significant drawbacks to this. Firstly, we'll be making a copy of a dataset in each account, which basically means we're going to be incurring greater S3 storage costs. And it's kind of unnecessarily so as well, because actually sharing the underlying data on S3 between accounts is really quite easy. You just need to set up appropriate bucket policies. Another problem with this is we're going to have to create, manage, and monitor all of these replication processes. And it's going to be difficult for our users to understand, is their copy of the dataset in sync? Where is the source of truth for this dataset? So with all of these problems, this wasn't really something we wanted to do either. So what we ideally wanted was to keep the distributed model, to have autonomy within our own accounts, to have our independent infrastructure, but to have some means of collaborating between these different accounts and clusters. So we thought we needed some kind of federation to provide at least an illusion of a unified cluster. So to do this, we built a thing called Waggle Dance. And I'll explain what it does kind of with reference to that first problem then. Those data scientists want, in their own account, wanting to access our core datasets in the main data platform account. So I've illustrated the data science account in that box at the top. And there they have their own metastore, and that's maintaining metadata about their local data sets that they're producing. And they have a workload there, and that workload might be a machine learning job, an ETL process, or perhaps some analytics tool. Now, that workload is talking to the metastore, finding out information about its data sets, and then it's using that information to read data from the S3 buckets that belong to the account. Now, what that workload really needs to be able to do is also read data from the S3 buckets belonging to the main data platform account. And as I mentioned, this is actually technically really easy to do. But the main problem here is the workload also needs to be able to retrieve metadata from the data platform account as well, the metastore there. And as I mentioned, Hive and the frameworks that use Hive have no means to do this. You can tell Hive to talk to one metastore or another, but there's no means to, there's no provision for concurrently talking to multiple metastores at the same time. Yeah. So what Waggle Dance is then is a request routing metastore proxy. So it implements exactly the same API as the Hive metastore. So as far as that workload is concerned, when it's talking to Waggle Dance, it thinks it's talking to a metastore. So the way it works then is that the workload will make metadata requests to Waggle Dance. Waggle Dance will look at those requests and work out which databases they relate to. And then it's going to forward those requests to the appropriate metastore. The metastore is going to return responses containing information about those data sets and pass that back to the workload. The workload is then going to inspect those responses, find out the locations for the underlying data of those data sets, and then read them from the relevant S3 buckets in either account. So what does this actually look like in practice for a user then? So here I'm using a Hive CLI example. So let's consider the siloed view first. So I go in and I want to see what databases are available to me. Well, if I look in the main account, I might see an ETL database, and that might contain our core datasets. And then if I do the same in the data science account, I might see some a machine learning database, which has all the datasets that are produced by our machine learning jobs. If I drill down a level, in those databases, we're going to have our datasets themselves, tables. So in the main account, I might have a core dataset, hotel, that describes all of the properties that we advertise on our website. And for simplicity's sake, let's just say there's a hotel ID and a string field for the name of the hotel. Now notice here that the location of that data is HCOM main, a bucket that belongs to the main data platform account. And similarly, in the data science account, we might have some machine learning job that figures out, okay, what's the best image to display for a given property? We call that the hero image. And that might have the hotel ID again and a string field for holding the file name of the best image. And notice here that the data for this table is stored in a different bucket, and that bucket, HCOM data sci, belongs to the data science account. So here we have two completely different data sets. They live in different clusters and in different accounts, but they're related. They both relate to these same hotel entities. So it's not inconceivable then that someone might want to join these two data sets. So how could they do that with Waggle Dance? It's actually quite easy. The thing that they need to do is that their workload client, they need to point that, not a metastore instance, but a Waggle Dance instance. And they can do that just with one configuration change. No code changes are necessary. So this Hive metastore URIs field, if you set that to the address of the Waggle Dance instance, then that workload is now going to talk to Waggle Dance. So once you've done this, what happens when you show databases? Well, now you get a combined view. So you're seeing the ETL database from the main account and the machine learning database from the data science account. And now that's working, you can do something more complex. So here I've got a join, so I'm getting the hotel name and the hero image for a particular hotel. And yes, this is a mock-up, but it does actually work in practice, and it works for all of our use cases. So this as well, we're only dealing with two metastore instances here, but Waggle Dance actually does support multiple metastores, and that's really useful for us because we have multiple brands and accounts. Okay, so our migration journey to this point then. We have our data scientists, our analysts, and our data engineers working in the cloud with our core data sets. We've given them means as well to migrate their own data sets off of our on-premises cluster using Circus Train. And we've also given them back the ability to share, explore, and discover data sets across the whole organization, just like they had on the on-premises cluster. But along the way, we've accumulated a bunch of problems. And the reason that this happened is because the adoption of these tools took us a bit by surprise, and it was a bit unplanned. So we ended up with these ad hoc deployments of Circus Train and Waggle Dance, and we got into a position where it wasn't really clear to us who was replicating which data set to where, which metastores were federated, which tools were talking directly to a metastore, which were going via Waggle Dance. So yeah, it was a complex environment. And as well, there was a lot of security and networking configuration required as well to make sure everything could talk to each other. So it's at this point something I think really interesting happened, and that was multiple architecture teams within our organization started to come up with patterns for the structured deployment of these services in accounts across the organization. And what I quite liked about this is that these independent teams have come up with pretty much the same solution. So this is the pattern they came up with. We call it apiary, and it's this grey box here. And the idea is that this is a single deployable unit, and that will go into every region in every data platform account. So the first thing to notice about this pattern is we have an instance of Circus Train there. Now that's there to do those migrations of the datasets from our on-premises cluster, but it's also there to do cross-region replication in Amazon as well. The next thing we have is a metastore service, and that's there to maintain metadata about those datasets that are produced and managed locally within that account. Now this is backed by a relational database that stores the actual metadata, and that's a very standard thing in Hive. That's part of Hive. But it's important because we run a second instance of the metastore service. And this is a read-only instance. And that's there to expose that metadata outside the account. Okay, so we don't mind sharing our datasets with other accounts, but we don't want them to do things like drop tables of ours and add new partitions and that kind of thing. So we want to lock it down and give them a read-only view. So that's what that's doing. Finally, the local workloads in an account, so they might be ETLs or analytical tools, that kind of thing, they don't talk to the metastore service directly. They instead go via a Waggle Dance instance. And that enables them to get a view of datasets and across the whole organization. So what does it look like when you start to apply this pattern across multiple accounts? So here I've got 3 example accounts horizontally, and I've done a deployment in 2 regions as well. So that's vertically US West 2 and US East 1. So this is meant to illustrate the 2 main objectives of this pattern. The first objective is to minimize our storage costs. And so you can imagine if I'm a user in a region in one account and I want to access a data set in another, what we don't want those users to do is replicate in the same region, because they're just going to be making an unnecessary copy. It's going to ramp up our S3 storage costs. So what we prefer them to do is federate across accounts. The next objective is to minimize data transfer costs. So now if you imagine a user in a different region wants access to a data set, what we'll actually do is we'll replicate that data set for them from the source region to their local region. And we do that because we don't want them to federate across region. Because what happens then is every time they run a query or they run a job, they're going to be pulling all of that data across region, and we're going to incur region transfer costs. So the final thing I like about this pattern is it gives us a predictable and consistent manner for the deployment of these services across our entire organization. And this makes it really a lot easier to configure and manage. And it's, as a user, if I go into whatever account or region, I'm not surprised. I know what I'm going to find. Finally, I think this pattern, I like it because it's made us think of our cloud architecture for our data platform and these tools in a different way. In all honesty, both tools were built as temporary workarounds to these inconvenient structures that had appeared in our cloud architecture. But once we had accepted that this really was going to be our architecture going forward, and we became comfortable using these tools, we were then more in a position to think of the opportunities that this gave us. So, first off, a couple of years ago, we had this problem. We've got to replicate all of these data sets. So this was a big burden, a bit of a headache. But once we got really good at doing that, we could then use the same pattern for doing disaster recovery. So we can now replicate data into a different region, and it's going to protect us against a region failure. And then these kind of multiple accounts that were appearing, at first it looked like they were going to inhibit our ability to utilize our data to the full. But once we had a solution for that, then we could then start thinking about these segmented accounts as a useful architectural primitive. So, if there was a good reason to put services or groups of users in a different account, then we no longer had to think about the impact it would have on our data platform. Okay, so that was our journey to the cloud. And if you're considering building a data platform in the cloud, then it's definitely worth remembering that our problems might not be yours. So we had a lot of legacy in terms of Hadoop file formats and existing data sets. We had this huge tool set that we needed to support and maintain compatibility with. And if you don't have those constraints, then it turns out that actually simple solutions can work really well. So I've seen tables migrated from an on-premise cluster to a cloud cluster just using simple create table as select statements. And also, we've got all these, you've got multiple metastore instances. But if you don't need that, if you can just have one shared metastore instance, then you should definitely do that, because it's going to make your whole data exploration and sharing piece a lot easier. So both of the tools we talked about today, Circus Train and Waggle Dance, we've open sourced, and they're available on the hotels.com GitHub account. I think the documentation there is pretty good, so if you do check them out, then we'd really appreciate feedback, either on our mailing lists or as issues raised or pull requests. Okay, so that's all we have for you today. We've We've got some stickers up front. You can also visit us at the Expedia group booth afterwards. And yeah, we've got time to take some questions.
In terms of cost, what is the difference between on-premise and cloud? So were the costs diminished or increased after you went to cloud?
So that's a very, very good question. It's also very hard to measure. And I don't think we have a complete answer for that yet because we're still in the middle of doing all of this. Kind of what I said at the beginning, like cost was a factor, but it wasn't our main reason for doing the migration. The main reason was really to be able to innovate faster, use new technology, be able to scale out quicker. So I think it was more, and these are costs that are very hard to measure, like the impact on our business of not being able to innovate at that pace. So that's more what we're looking to get out of the cloud as opposed to reducing our data center costs. So definitely, like at our stage in the cloud migration, the company hasn't been like focused on cutting costs. It's more like focus on using the cloud to do things better. So that hasn't really been a point. One thing, though, that we have seen in the cloud, if you don't monitor your costs, things can get a little bit crazy quite quickly. So we've had to institute a lot of policies that we never had to worry about in the past, where everything that we deploy in the cloud needs to be tagged in a certain way so that you can tell which team tagged it. And then we're running reports all the time in the background. You can also set certain thresholds and limits that if things go above what you would normally expect, you get alerted or things get shut down. But we've had to focus a bit more on that, but that hasn't been our primary concern. So I guess there were a couple of reasons why we didn't do that. So firstly, some of those jobs that produced the datasets weren't under our control, so we couldn't. We then also didn't want to have to modify. So also those jobs, again, are written in lots of different frameworks, languages, and so on. So we'd have to come up with whatever that replication bit is to tag onto the end of them in all of those different tools. And we'd have to coordinate across all those teams. All those teams would have to change their processes. I guess a scary thing when a company like us that's been running for a long time, there are certain jobs out there that no one actually knows how they work anymore, and you don't want to change them. So those are a lot of reasons. And yeah, so then your point on what's going to happen when you migrate the jobs. Some of them you can actually just lift and shift. So if you have a Hive query that's selecting into something, it's actually abstracted away from the underlying storage already. And if you just move it somewhere else, you can actually just move it and you don't have to change it much. Some of our other jobs, like MapReduce jobs, should be able to just move them over to EMR and maybe just change the file locations. So for the most part, we didn't think it was worth changing all those jobs, and we would have to change them again when we moved them. But it's definitely something we thought about.
So, I guess the on-premises stuff will just kind of shrink and maybe some of the really weird stuff that no one understands will just stay there.
Yeah, it'll either stay there, we'll lift and shift it, or it'll be re-architected and rewritten in something completely different. Sure.
You ingested data on-premise in the HDFS and replicated into the cloud. How quickly was the data transfer from your on-premise into the cloud? So how quickly before was available for the scientists to use?
So this is also something that evolved over time. I think when we first started, I don't remember all the details, but a lot of those data transfers were going over the public internet. And then we set up interconnects between our data centers and we use a provider like Verizon, AT&T, and they have these massive pipes between different data centers. So I think we had like a 10 gig link, and that went up to a 40 gig link. So we have these very big links set up between on-premise and the cloud. But that was a key part of doing this, because we were starting to saturate the public internet link. And then there's a lot of complexity here that, to be honest, I don't understand all of it. But depending on where you start your jobs from, they go over Direct Connect, they might go over these links or over those links. So we spent a lot of time figuring that out. Another very important thing was where we ran our jobs from. So kind of what I said in my earlier on was, if we ran them in EMR, we could immediately get slots to start copying the data over. And once we had the 40 gig link in place, the data would get over very fast. We have a bunch of graphs with the timings. They change over time depending on what's being replicated when. But typically we can get terabytes of data over fairly quickly. So the latency of the data arriving in the cloud is, maybe minutes or hours, not days. And for most of our use cases, that's good enough. But that was definitely something we had to think about. A lot of our data processing is still batch, and we have a real-time streaming platform where what you're talking about, I guess, people getting access to the data really quickly is much more important. And that was one of the things we've decided to build sort of cloud native from the start, so we don't have data latency problems for those use cases. Anything else? No? Good. Thank you very much.